Okay, so this is the third video in our current series, and we're going to continue looking at a similar type thing that we were looking at last time. So this is called stimulated emission, and we're just going to start by looking at something that should become quite familiar to us. Okay, so what I've got here is I've got two energy levels. I've got a lower and a higher. Okay, so the first thing we're going to look at is absorption. Okay, so we saw last video that when we get a photon come in that corresponds to the energy of this level here, we can get our photon absorbed and it will kick our electron that's in the lower state up into the higher energy band. Okay, so once we've done that, we've absorbed it, our electron is now in the high energy band, and we get what we call spontaneous emission. Okay, so with spontaneous emission, we get our electron has been excited into the higher state. We drop back down just after a certain amount of time, depending on what atom it is, and we emit a photon that's identical to the one that stimulated us up to the high energy state in the beginning. So that's what we looked at last time, and that should be getting familiar for us now. So that's what we call spontaneous emission. Now we're going to have a look, and you can see from the title here, this is stimulated emission. So we're going to have a look at that now. Stimulated emission. Okay, so again, I'm going to have two energy levels here, and this time I'm going to indicate what color? In green. The energy from the top to the bottom, we'll call that energy E. So I'm hoping that comes up. That says energy E. All right. So what happens is if we have an electron sitting in the high energy band, and we get a photon come in, okay, and that photon has energy E as well, so that matches the gap between our lower and our higher band. What we get is something really interesting. So our electron is stimulated by our photon to drop down, and what we get on the other side is our original photon, and we get a stimulated photon as well. So what we get is we get two identical photons. All right, so we've sent one in and we've stimulated that emission, and we've got two identical photons out. Now, these are identical. What I mean is they have the same direction. Okay, they have the same phase, and they have the same frequency and wavelength. Okay, now because they have the same frequency and wavelength, that means they also have the same energy, and this is the idea that allowed us to create laser light, and we're going to explore that later in this video. So this stimulated emission is a really important idea, and like I said, the one that we use to produce laser light. Now, to produce laser light, what we need is a population inversion. Okay, and we're going to have a look at what that means just right now. So, population inversion. So I'd like you to take this down. So a population inversion is produced whenever there are more atoms in a higher energy state than in a lower energy state. Okay, so what that means is if we draw our energy levels and we're looking at some electrons, and I'll just represent those by dots. So to have a population inversion, I might have some in the lower energy level, but what I'm going to have is more of them in the higher energy. Okay, so this isn't normal, and that's why it's called a population inversion. Okay, because most of them are up. So what we need is the majority of our electrons to be in this higher energy state. Okay, so that's why I've highlighted there are more atoms in a higher energy state than in a lower energy state. Okay, so if population inversion occurs, what we are going to get is more stimulated emission than absorption. Okay, so just throwing back to our previous slide. So if we have a population inversion, most of our atoms in an excited state, we're going to see more of this stimulated emission, so producing double identical photons, than the absorption, where we just absorb one and then one is emitted. Okay, so we need population inversion for more stimulated emission than absorption. So in most atoms, we don't actually see this. Okay, it's a very special type of atom that we must have for this to be seen. Okay, so now to see this stimulated emission, we have to have our excited states last for a long time before spontaneous emission occurs. Okay, so most of the time, what happens is if we get an electron in a high energy state, it just spontaneously emits pretty quickly. So what we need is this electron up here to be able to stay there for a long time. Okay, so some states do actually last for a long time before that occurs, and what we call these is metastable. Okay, stable, like its normal definition, just means it's going to last there for a long time. So we call those a metastable state. Now, for population inversion to occur, all right, so just going back to our population inversion, so for us to get more electrons in the higher energy band, we have to have this band. This band has to be metastable. Okay, so the electrons that go into that band have to last there for a long time. So the higher energy state must be metastable for population inversion to occur. Okay, so that's really important, and just like you to take these notes down. So what we're going to do now is have a look at the application for this topic, and the application is lasers. Okay, and we're going to look at particularly what we call a helium neon laser. All right, so first we're going to have a look at the properties of helium and neon. So helium, between its ground level and its first energy level, we have a gap of about 20.61 electron volts. Okay, and if you have a look at neon, between its ground state and its third energy state, we've got a very similar energy, so 20.66 electron volts. Okay, so we've got this very similar energy level gap between for the helium and the neon. And what we also have is a neon that has a third excited state that's metastable, and we're going to see why that's important in a minute. So basically what we're going to get is helium. It's going to have an electron in the ground state, and we're going to stimulate emission somehow, and I'll talk about that again later. So what we get is our helium, our electron is stimulated to the top, and what it does is it collides. So I'm going to write it collides, and what that does is transfers energy to the neon. Okay, and what that results in is a neon having an electron in the third excited state. Okay, now what we've got is a metastable state with an electron in it. So what happens next is we get a photon come in, which kicks our electron down. Okay, and we know stimulated emission, we produce two identical photons. Now the energy level gap here corresponds to, I'll just write that in, delta E. The energy level gap is 1.96 electron volts. Okay, and what that corresponds to is, if you do the math, is red light. Okay, so we're going to have, if we put some red light in, we're going to have two photons of red light come out. Okay, and this is we're going to use this process and discuss in a minute how lasers work, but this is just the start of it. Okay, so the energy difference between the third and the second state results in red light being emitted if we put that in. So for this to work in real life, we need some components as part of our laser, and we're going to have a look at what they are now. So components for this actually to work, or for this to happen, is one, we need an active medium. All right, so that's just talking about our helium and neon. So here we've got our helium and neon, and that's going to act as our medium for this to happen. Okay, so without it, it wouldn't work. The next thing we need is a pump, and I put that in quotation marks because it's not a pump like you'd pump a soccer ball up with. It's a pump that supplies energy to excite atoms. Okay, so we need to excite atoms from this ground state up to the first excited level, and usually we do that with electrical discharge. Okay, so we need an active medium, a pump, and third of all, we need mirrors at each end of our laser to amplify the laser light. Okay, so if this is our laser here, we'd have lasers at each end. Mirrors at each end. So our red light would be produced, hit one side, and be reflected, and go either side. So the reason we have this is because we want to get our red laser light hitting as many of these excited electrons in the metastable state as possible. So if we keep them in there, we're going to keep getting those emissions. Okay, so just take this down. These are the three components we need for a laser to work. Okay, and just quickly, we're going to finish off with just the uses and the safety aspect of the laser. Now, I'm not going to go into too much depth, but basically we've got hundreds of uses of a laser. We've got LADs, CD player, DVD player, barcode scanners, laser surgery, and laser cutters. So we've got a few of these in the school. And the safety aspects, because it's a high intensity light is produced, it can damage sensitive tissues in your body. So can damage sensitive tissues like your eyes. So obviously you never look at a laser because that can cause damage. All right, so that's the end of this section.